Over roughly 4.6 billion years, Earth has kept rotating almost without interruption. There were surely days it wanted to rest, yet through rain and wind it never stopped spinning, maintaining the baseline dynamics that underpin climate, oceans, and life. Now, what happens if we meddle with this steady rotation using external power and dramatically accelerate Earth's spin? For example, what if we made Earth's rotation 20 times faster? Such a change would not just shorten the day, it would cascade across geophysics, atmosphere, oceans, technology, and society. If Earth spins faster, does that simply mean shorter days? Or does it lead to catastrophic outcomes? In this episode, we'll explore what happens if Earth's rotation becomes 20 times or more, considering both near-term mechanical impacts and longer-term system reorganizations. First, today's baseline. Earth rotates once every approximately 24 hours around its axis, tilted approximately 23.4 degrees to the ecliptic plane. From Earth's diameter, the equatorial rotational speed is approximately 1,600 kilometers per hour. If a high-speed train tops out around approximately 320 kilometers per hour, then a person at the equator is moving at about 5 times that speed, even while standing still relative to the ground. This spin also shapes sea level and the geoid via centrifugal effects, subtly flattening Earth into an oblate spheroid. So, why does Earth rotate at all? The answer goes back to early formation. Gas and dust in space swirled together to form proto-Earth, and angular momentum was carried forward. Earth has been spinning ever since. In space, little opposes rotation, so inertia keeps it going. The sun and moon's gravity act on Earth, but not in a way that stops the spin, so its speed barely changes. Over long time scales, tidal friction, drag from tides, and climate system dissipation cause the spin to slow slightly, lengthening days by fractions of a millisecond per century. Of course, Earth won't become 20 times faster on its own. We'd need external forcing. Let's imagine ramping Earth's rotation up toward Jupiter-like rates, the fastest spinner in the solar system. Jupiter's diameter is approximately 143,000 kilometers, and its equatorial speed is approximately 45,000 kilometers per hour, approximately 27 times Earth's present speed. While Earth cannot actually match Jupiter's gas giant behavior, this target helps illuminate thresholds and failure modes. What if we increase Earth's spin gradually? A sudden jump yields only disaster, not useful testing. So we'll accelerate slowly and watch impacts emerge step by step, allowing partial adaptations while still revealing hard physical limits. First, we'd see seawater accumulate near the equator. With increased centrifugal force, the equatorial sea level rises, centimeters scale, inundating ultra-low-lying coasts and deltas earlier than elsewhere. Even as Earth's spin changes, satellite orbital periods don't. They depend on orbital radius and Earth's gravity, which means orbital models drift, and geostationary satellites, whose orbital period matches Earth's day, appearing fixed over one longitude, lose the premise of stationary. Expect degraded positioning accuracy, wide-area satellite communications failures, and mandatory orbit corrections, redeployment rock relaunches, with major economic impacts across navigation, weather, broadcasting, and emergency services. Critical infrastructure resilience would be tested at a global scale. As Earth's rotation accelerates, civil time itself becomes a design problem, since clocks synchronized to solar days would need continual adjustment or redefinition, complicating aviation slots, power grid cycles, financial markets, and international coordination. Keep accelerating and things turn critical. As spin increases, apparent weight decreases. The weight we feel is the vector sum of Earth's gravity and centrifugal force from rotation. Centrifugal force points outward, counteracting gravity. Thus, faster rotation means lower weight. Even today, equator versus poles show a difference. Equator readings are approximately 0.5% lighter than polar readings due to stronger centrifugal force. A slight weight loss may feel nice, but not for long as structural and physiologic margins are crossed. As spin rises further, massive equatorward seawater redistribution drives equatorial sea level rise, submerging low-lying equatorial lands and making them uninhabitable. Simultaneously, atmospheric wind belts change dramatically. Currently, the northern hemisphere has westerlies, west to east, and the southern hemisphere has trade winds, east to west, largely due to the Coriolis effect. Because Coriolis scales with rotation rate, faster spin stronger winds. The effects go beyond westerlies. Super typhoons, tropical cyclones, would become more intense and frequent, with larger eye walls and longer lifetimes. Cyclones' vortex structure arises because Coriolis acts toward the eye. By analogy, Jupiter's Great Red Spot, a long-lived giant vortex, owes much to its extremely rapid rotation. A Great Red Spot-like megavortex on Earth cannot be ruled out, especially over warm, deep ocean basins. Aviation and shipping would face transformational hazards, with jet stream shifts, extreme wind shear, rogue waves, and corridor closures, driving up costs and risks while straining global logistics. Spin-up also affects geomagnetism, Earth's magnetic field. The field is generated by electromagnetic fluid dynamics in the solid conductive inner core and liquid outer core, the geodynamo. The outer core circulates under thermal/compositional gradients and rotation, generating currents to the magnetic field. Research suggests a few percent changes in rotation can produce approximately 10 to 30% magnetic field changes, noting the timescales are tens of thousands of years. Short-term visible shifts may be limited, but long-term structural/intensity changes could accumulate. Magnetic field variability influences cosmic ray/solar wind shielding, ozone chemistry, and space weather resilience of satellites and grids, raising societal risk. Increased rotation could also modulate core convection patterns, potentially altering secular variation of the field and polar wander, with knock-on effects for compass navigation, pipeline corrosion rates, and auroral zones. A faster spin means stronger Coriolis, reorganized atmospheric circulation, accelerated redirected ocean currents, migration of rainfall belts, and phase shifts in monsoons, a system-wide climate relayout. Equatorial seawater bias and polar water budget changes would redraw coastlines, submerge deltas, and trigger large-scale salinization and soil degradation. Agricultural belts would be forced to shift latitudinally and altitudinally, disrupting food supply chains and water management regimes. Urban systems would need re-engineering, storm drainage, coastal defenses, building codes, and heat risk mitigation, while insurers and governments grapple with unsustainable disaster exposure. How far until systems break? In theory, at extreme spin, centrifugal force nearly cancels gravity at the equator, so effective gravity drops sharply. Solid Earth would increasingly bulge into an oblate spheroid, larger equatorial radius. Consequent stress redistribution in the crust might reorganize seismic activity regions and volcanic responses. In extreme cases, near floaty conditions at the equator would invalidate core assumptions of architecture and urban design, requiring tethered structures, new anchoring systems, and rethought mobility. Human physiology would also be challenged. Changes in effective gravity, Heat stress from altered circulation and airborne particulate dynamics could strain cardiovascular and respiratory systems, demanding protective design for workplaces and transport. In summary, even gradual acceleration would reassemble landforms, wind systems, ocean currents, satellite infrastructures, and social systems. Extreme acceleration would alter the effective gravity field and transform Earth's coupled systems. Earth's rotation rate is the baseline of our life, technology, and ecology. And 20 times or more is a change that would simultaneously surface environmental, economic, and security risks, forcing civilization into permanent adaptation mode. That's all for Curiosity Science. See you next time.